Hello. In this C programming video, we're going to be getting into dynamic memory allocation, specifically the Malloc, Calloc, Realloc, and free functions. The program we're going to make here is going to serve as a comprehensive guide to the four primary functions for managing memory dynamically on the heap in C. Dynamic memory is essential when you do not know the exact size of your data, like an array or list, until the program is actually running. Um, Definitely, this tripped me up when I first got into C programming. It's a very distinct topic that I would like to cover here to um, get you familiar. The goal of this video is to be a good resource for you to provide yourself with the tools to manage memory effectively, which is very important for more advanced C programming. This directly addresses a core challenge in C and offers you practical skills that you can immediately apply. If you find these sorts of C programming videos useful, please give them a like. Really helps out the channel. Comment with any questions. Otherwise, subscribe to not miss future programming tutorials like this. But let's get started here in our program. So first thing we need to do here in our program, as always, is to include our relevant libraries. So in this case, we need the standard input-output library for mainly printf, and then we need our standard library for those, especially those four functions: the uh, malloc, uh, calloc, realloc, and free. So the first function we're going to kind of demonstrate here is the malloc function. It's the memory allocation function. The purpose of this is to allocate a block of memory. The return value is always going to be a void pointer and null on failure. There's a great importance here of typecasting and checking for null. A simple example would be allocating memory for an integer or a small array. But we're going to write a function here to kind of demonstrate the topic. We're going to call it, it's going to be a void, we're not returning anything, and we're going to call it demo malloc. And there's nothing we're passing in. Um, First thing we're going to do is, we're going to print a header here. But after that, um, the purpose of this function is going to be allocating a single block of memory of a specified size in bytes on the heap. The memory content is uninitialized. It contains whatever random data is left there, often called garbage. So we're going to allocate memory for the size of an array. So we need to first declare that with an int. We're going to call it int size of array, and let's just say the array is going to be five long. So the core malloc call is first we need to ask for 5 blocks, each the size of an integer. So that's where we're going to use the size of function. Malloc returns a generic void pointer to the start of the memory block, and we need to use the type cast to tell the compiler the pointer points to an array of integers. So we're going to do int, and we're going to call this int pointer array pointer, and we're going to make it equal to first the typecast, and then the malloc function itself, and inside here we're going to pass in the size of the array times the size of an integer. So we're going to just use size of and then int. Next, we need to do a critical safety check. The operating system might fail to grant the request if memory is scarce. If it fails, malloc is going to return null. So we need to check that for safety. So we're going to do if array pointer is equal to null. We're going to print out an error. And then we're going to return. because it's not good to continue at that point. Next, we're gonna actually, use the memory. So we're gonna say that we successfully allocated specific number of bytes on the heap for an array of a specific number of integers. Obviously, we're gonna use format specifiers here. Two, the first one is going to be casting to int. The size of the array times the size of the int. And then the second decimal is going to be the size of the array. Because again, this is just calculating the number of bytes. Next, we can now use the pointer like a regular array pointer, which is a pointer arithmetic shortcut. So we're going to print that we're initializing the array values, and then we're going to use a simple for statement. So for int I equals 0, I is going to be less than 2, I is less than the size of the array, and then we're going to increment I. Here we're going to make array pointer at index I. We're going to make that equal to I plus 1 times 10, just as an example. And then we're going to say what we set the array pointer to. So first decimal is going to be just I, because for the display purposes, and then we're going to do array pointer I, just for display purposes there. So important note at this point, we're not going to call free. We're going to talk about free later in the video. But we rely on the main function to keep this pointer alive for the Realloc demonstration. But we're going to print that the demonstration is done, that this demonstration is done. Okay. Our next demonstration is going to be the contiguous allocation demonstration, or the Calloc. So the purpose of this function is to allocate memory for an array and initializing it to 0. The key difference here is 0 initialization and arguments. An example would be to allocate memory for an array of integers and demonstrating 0 initialization. So here we're going to make a new function here called return type void demo calloc. We're going to print our header here. So the purpose here is similar to Malloc, but it's going to take 2 arguments and initializes all memory bytes to 0. This initialization is a key difference and often safer for number arrays. So first we're going to declare an int variable called num elements, and we're going to make that equal to, let's just say 3 this time. And now we're going to do the core call. So the first argument is going to be the number of elements, and then the second argument is going to be the size of each element. So we're going to do an array of floats. So float array. We're going to make that pointer equal to, first we're going to need the cast, and we do the actual function call. And then the 2 arguments here, first is the number of elements, and then the second argument is the size of each element. So size of float. And then we need to do a similar check here to see if the array is null. If that's the case, we need to just return at that point. So if float array, that's equal to null, we're going to print an error, and again, then we're going to return. And in here, we're going to demonstrate the zero initialization feature. So we're going to do printf. So we're going to allocate how many elements? Well, num elements. And then we're going to use the for loop to go through the function just to show that. So we're going to do for int I equals 0. I is less than num elements, not num pointer, and then I plus plus. So here we're going to just print out both the index and the value of the index. So we need D for decimal and then F for float. And that's all we need inside the for loop. And then finally, we're going to do some immediate cleanup here since we don't need this memory block anymore. So we're going to do free float array. We'll get to more about free later in the video. And then we're going to print that we are done with this demonstration. All right. Our next demonstration is going to be the reallocation demonstration, or Realloc. The purpose of this is to change the size of an already allocated memory block. The scenarios for use would be expanding or shrinking memory. An important consideration here, well, there's two important considerations. First is to handle a null return and for potential data movement. An example would be to expand an array allocated with either Malloc or Calloc, the two previous functions we demonstrated. But with this, we're going to do another void function. Here is going to be demo realloc, and then we're going to pass a pointer to a pointer, so 2 asterisks, so we can modify the original managed pointer variable in the main function, which we'll get to if the memory location changes. So we're going to pass it in int 2 asterisks pointer to pointer. First, we're going to print our demonstration header here. Next, we're obviously the purpose of this is to change the size of the memory block already pointed to by pointer to pointer. So we need our 3 variables here. First is the old size. The old size here is going to be 5. And then let's say the new size is going to be 8. So int new size is going to be 8. And then finally, we're going to store the original address for easy reference. So we're going to do int original and then pointer, int original pointer. We're going to make that equal to pointer to pointer. So first, we're going to print out the original array size. And then we're going to say what we're expanding it to. So old size to new size. And then we're going to print out the original data here. No need to use a loop for this. We'll just do original pointer 0, 1, 2, 3, and 4. And then we're going to reallocate the memory block. So the first argument here is the pointer to the original memory block, and then the second argument is the new total size required. So we're going to create an int pointer called new pointer. We're going to make that equal to, first, obviously, just like the previous two, we need to cast, and then our function call. So again, the first argument is the original pointer in this case, and then the second argument is going to be the total size required. So that's going to be the new size times the size of an integer. So we need to do another critical safety check here to see if the reallocation fails. If it fails, it's going to return null, but the original block is still valid and unchanged. So we need to do see if the new pointer, if that is equal to null, we're going to print out an error statement, and then we're going to return. But otherwise, we can continue. So at this point, it's a success. If the memory location changed, it often does when expanding, the new pointer will hold the new address. So we're going to update the main pointer. So we're going to assign pointer to pointer. That is going to be equal to new pointer. So at this point, the reallocation is successful, and the data is going to be preserved up to old size of the elements. So we're going to print that out. Then we'll print out, pass in the old size. Next, we're going to demonstrate the data preservation for the first 5 elements and a new uninitialized space. So we're going to use it. We're going to use the for loop. So for int I equals 0, we're going to make I less than the new size, not new pointer, and then increment I. Inside here, first we need to see if I is less than the old size. So if I is less than the old size, we're going to print out the element, the preserved element. So we're going to do print f using 2 decimal format specifiers here, element at index I, and then we're going to print out the value, which here is going to be pointer to pointer at index I. But otherwise, if I is not less than the old size, in other words, if it's at old size or above, we need to do a little more work. So the new elements are uninitialized or garbage. But we're going to just print that out just to show you. So again, the similar format, I, and then pointer to pointer, if I can type, at index I. And then at this point we will initialize the new elements. So we're going to do pointer to pointer I. We're going to make that equal to I plus 1. Similar last time, but let's just do 100. Again, that part really doesn't matter. So now we can print out the new initialized value at that particular index. So I, and then same thing, pointer to pointer at I. So once we are done with all of that, with actually demonstrating the data preservation, we're done with this demo, and we will print that out. So this brings us to the final function here that we're going to demonstrate, free or deallocation. The purpose of this is to release dynamically allocated memory back to the system. This is very, very important for preventing memory leaks, but there are dangers of double freeing and dangling pointers, which we'll get to. Here we're going to demonstrate free after each allocation example. So let's get started with our final demonstration. Instead of demo, we're going to call this free all. And then inside here, we're going to pass in the pointer, an integer pointer. We're going to print out our header. First thing we're going to do here, The purpose of this is to return the memory block pointed to by the pointer back to the system heap. Again, this is very important. You always have to do this because you need to use for all memory allocated by Malloc, Calloc, or Realloc to prevent memory leaks. The best practice is to only try to free a non-null pointer. So, keeping that in mind, we're going to see if the pointer is not equal to null, we're going to free the pointer, just free. That's the function declaration. Then we're going to pass in the pointer, and then we're going to say that we release the memory. So printf. So memory block at address using p or the pointer. So we're just going to cast in pointer to avoid pointer. So another critical safety check here. After freeing, we're going to set the pointer to null. And I'll get to that in a second. So we're going to do pointer. We're going to make assign that to null. This is very important because this prevents a dangling pointer, which means a pointer that still holds on to an address to memory that is no longer valid or owned by the program. And we're going to let the user know that we did this. So now that we finished all 4 of our demonstration functions, let's now get into our main execution with int main to actually show this off. First thing we're going to do here is we're going to print out our header. Next, we're going to declare the single main pointer we will manage throughout the program. So we're going to call this int pointer managed pointer, and we're going to set it to null initially here. And then first we're going to call our demo Malloc function. And then next we need to set up for the reallocation. We're going to rerun Malloc here to get a fresh pointer to pass to the reallocation demo. So we're going to do that with managed pointer. We're going to make that equal to, first off, casting, and then Malloc 5 times the size of an int. So if the managed pointer is not equal to null, we are going to initialize the data so the reallocation can show preservation. So we're going to do for int I equals 0, I less than 5, and then increment I. We're going to set managed pointer I to be equal to I plus 1 times 10. And then at that point, we're going to let the user know that we managed the pointer successfully and it's set up for the demo. At this point, we can call the Calloc demonstration. And then we're going to do the reallocation demonstration. So we're going to do that with, first of all, we need to pass in the address of the pointer if the managed pointer is not equal to null. So we're going to do if managed pointer, if that is not equal to null, we're going to do the demo for reallocation, and we're going to pass in the address of the managed pointer. But otherwise, if it is null, we need to skip it because the managed pointer cannot be allocated. again, it's always good to check to see, do these sorts of checks. Get in the good practice doing that now so you don't run into bugs in the future. Finally here, we're going to do the free demonstration, which is our critical cleanup. So free all, and then we're going to pass in the manage pointer. And then at that point, we're going to say that all of our dynamic memory operations are concluded and the program is finished. So I hope that this was a good demonstration on how to do this. At this point, let us demonstrate the function here. So we're going to open a new terminal. Only if I would do double check my errors here. But we're in our terminal. We're going to do GCC. We call this program Dynamic Memory Allocation.c. We're just going to call it Dynamic Memory Allocation. That's going to compile, and now we can run it. So getting into the function here, first is our demonstration. So first we initially allocate 20 bytes on the heap for an array of 5 integers. That makes sense. Then next we initialize our array values, and at that point we are ready for the reallocation demo. Next is the Calloc demonstration, the continuous allocation demonstration. We are allocating 3 elements with Calloc and showing our initial values. They should be 0.0, and as you can see they are. The memory was successfully freed immediately after use because we're not using that float array anymore. Now moving on to Calloc. As you can see here, the original array size is 5, and we're attempting to expand to 8 elements. And then original data before the reallocation is that reallocation successful. Data is preserved up to 5 elements. So 0, 1, 2, 3, and 4 work out fine. But getting into element 5, it's obviously not 0. That's a garbage value. But then we initialize it to 600. Obviously, this number is a garbage value for element 6, so we change it to 700. Likewise, this garbage value, we change it to, or initialize it to 800 for element 7. And then the reallocated memory is ready for final cleanup. And then our free demonstration here, the memory block at address, this address has been successfully released, and we set the pointer to null to prevent dangerous dangling pointer bugs. And at that point, all dynamic memory operations have concluded and the program finished. So I hope this video was a good introduction to dynamic memory operations, specifically memory allocation, contiguous allocation, reallocation, and memory release. If you have any questions, please comment. If you found it informative, please give it a like and subscribe to the channel to not miss future videos like this. Otherwise, thank you for your time in watching this video, and have a great day.